Okay, I want to look at two questions from the notes on Chapter 2, Section 2. And this was a question that we posed in class. We said, can we actually prove that the limit of 2 of x, 2 times x, as x approaches 1 is 2? And obviously, it's true. We can draw the graph and see it, but suppose we wanted to prove. And so I wanted to kind of take this opportunity to go into what this limit means. And so we said that one way of thinking about what it means for a limit of a function to exist is we think of kind of like a car crash. And I'm going to illustrate this idea by using a different example. I'm going to look at the limit as x goes to 2 of 3x, which we know already from the material we covered today is going to be 6. But we're going to show this. So here's what the definition of a limit actually means. First of all, here's x equal to 2, y equal to 3. We know that our function looks like this. I'm going to put a little circle here. And what it means for this limit to exist is, if we go back to this analogy of a car crash, it means that if there's a car coming from this direction, from the right, as its x-coordinate approaches 2, its y-coordinate approaches 3. And by the same token, the car is approaching from the left here. As its x-coordinate approaches 2, its y-coordinate approaches 3. So both of these cars are approaching the point 2, 3. Now, here's the idea behind the limit. This is the key idea. So suppose I make this claim. The limit as x approaches 2 of 3 of x is equal to 6. You get to challenge me. And you say, okay, if both of those cars are really approaching this point, then that means that their y-coordinates are approaching 3. And we recall what it means for something to approach a number. It means I can get as close as I want. So you challenge me and you say, if that's really true, then you should be able to get some certain distance from 3. And you get to name how close you want me to be. And I'm just going to give this some name. I'm going to make up a name. I'm going to suppose that, let me go back. I'm going to draw this little band around 3, and you're going to require me to get both of the y-coordinates to get within this little band. And I'm going to say that this band it's like a tube. It has width h. Okay, so this is a tube of width h. So you get to tell me how small you want that h. You say, okay, you're really converging to 6. Whoops, this should be 6. You're really converging to 6. Then you should be able to get within the y-coordinates for both of these cars should be able to get within small h of 6. And what I have to come up with is I have to come up with some little band around 2. And I'm going to call the width of this band, let me just call it, we'll just make up something. We'll just call it M. Okay. And what it means for a limit to exist is you give me this H band around 6. And I have to give you this, for lack of a better word, we'll just say M band around 2. Such that when the x-coordinates of the cars are within my M band, they're within your H band. And that's what a limit means. It means that you tell me how close you want the y-coordinates to be from as the cars approach from both sides, and I have to give you some little band around the x-coordinate I'm approaching, such that when the x-coordinate of the cars are in this band here, they're within M of 2, the y coordinates are within h of 6. And they stay within h of 6. Okay? Anywhere in this m band, they're going to stay within the h band. That's key. So once the x coordinates are within that m band, the y coordinates are trapped within that h band. They can't go further away. So what I want to show, if I was going to try to do this proof, here's what I would try to show. I would try to show that for any given h greater than 0, I can come up with some with m greater than 0, so that when x is in 2 minus m, 2 plus m, in other words, when the x is in this, what we'll call m band, then this guarantees that f of x is in this h region. And I'm going to prove to you that I can find such an m band. So you give me any h you want. Let's just let h be arbitrary, okay? So let h be any number greater than 0. I claim that m equal to h over 3 will work. It will satisfy this condition up here. And let me go ahead and show you. So suppose I'm in this m band, okay? What does it mean? Well, it means that 2 minus m is less than x is less than 2 plus m, right? That's what it means to be in this m band right here. And now I'm going to substitute in this h over 3. So this means that 2 minus h over 3 is less than x is less than 2 plus h over 3. And now I'm going to multiply through by 3. I'm going to multiply the entire inequality through by 3. So I'll get 6 minus 8 is less than 3x is less than 6 plus 8. And notice this is exactly what I want. This is the function. So now this tells me that if the x values are within the m band, the function values are within the h band. Now, this particular function happens to be a linear function, so finding that little m band for a given h band is not that bad. But in general, it can be really difficult and tricky. And that's one of the reasons why we like those limit laws in Section 3 of Chapter 2 so much, because they don't require us to actually formally prove something like this. Okay. So the last thing I want to cover is this example we did in class. We want to look at the limits from both sides. And essentially what we're going to do is we're going to use the fact that the limits for both of these, let's go ahead and look at the limit as x approaches 3 from above of 2x over x minus 3. And I can go ahead and I can just make a little chart here, okay? So x approaches 3 from above, I'm going to make a table, x and f of x. And so I can start at 4, and if I plug 4 in, I'm going to get 8 over 1, which is 8. And now I'm going to be kind of smart. I'm going to realize that if I use fractions, 3 plus a fraction, this will be kind of easy to evaluate. So let me go ahead and use 3.5. So what I'm going to get up here is 2 times 3.5, which is 7 halves, over 3.5 minus 3, which is a half. And I get to flip this half, okay? We never divide by fractions, we multiply by the reciprocal. And when I do this, I'll just flip it. Let me go ahead and try this. So let this be... before we said you reached the value of 8. And to get 3.5, we're at 14. That's pretty high. Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. You can see this is going to be hard to graph actually, because we're going to start down to 5. And you might guess that as x approaches 3 from above, this is going to go to positive infinity. And if you think about it, we really don't have to do any more calculations. It's kind of obvious, because if you think about it for a second, as x approaches 3 from above, the numerator is approaching 6. And as x approaches 3 from above, this is approaching a small positive number. And of course, it's getting smaller and smaller as x is getting closer and closer to 3 from above. So therefore, this function overall is getting larger and larger. So we totally expect that this function is going to converge to positive infinity. All right. By the same sort of logic, without even making a table at this point, we can deduce that the limit as x approaches 3 from below is minus infinity. And the reason why is if you think about what the numerator and denominator are doing, this is going to 6, and this is going to a small negative. Why is it negative? Because x is approaching 3 from below, so x is less than 3. And of course, the closer we get to 3, the smaller that number is, it remains negative, and therefore the larger this quantity gets, but it becomes negative. So x equal to 3 is a vertical asymptote. But the limit does not exist, because the one's going to positive infinity, the other's going to negative infinity.